Alright, welcome back. So we had just finished looking at static magnetic fields, and in this video we're going to look at Maxwell's equations. And it's funny to call this Introduction to Maxwell's Equations because it seems like we've talked about Maxwell's equations before, and we have, except we weren't talking about them in the most general sense. We're talking about them in the static sense. So now we are going to begin to look at changing magnetic fields and changing electric fields, and they're actually one and the same, called the electromagnetic field. So let us begin to take a look at this. So just to summarize where we're at and how we got here, I want to recall that stationary charges, they produce did I spell that right? Yep. Stationary charges produce electrostatic fields. So this is what we looked at, electrostatic fields, at the beginning of the term after we did the vector analysis. We looked at electrostatic fields, Gauss's law, Gauss's law and Coulomb's law. Then steady currents. I'll point out that steady currents, they produce magneto-static fields. Okay, and then so after we looked at electrostatics, then we turned our attention to magnetostatics, and we talked about, for example, how a long current carrying wire produced a magnetic field, but the current in that wire was not changing. Now, where we're going with this now is that a time-varying current or accelerated charges produce electromagnetic fields, what we call waves. So a wave here, when I say wave, that means electromagnetic field, and vice versa. So for example, we showed that if you have a loop of current carrying wire, let's say centered at the origin, resting in the XY plane, like this, and we'll say that the current is going this way, and if it's steady, meaning that the current I does not change, then we said the magnetic field points like this. Okay, so now let's say that I turned that current on and off. So maybe the current versus time, so that current is I, maybe the current versus time looks something like this. It's at I, and then it's off, so it's 0, and then it's I, and then it's off. So something like this would be like a digital signal. All right, well then what would happen to the magnetic field? Well, the magnetic field would change between this H that I've drawn along the z-axis and 0. It would be H here, right? And then there would be 0 magnetic field there, and there would be H here, and then there would be 0 magnetic field. So this is a change in magnetic field then, and this, as we will see, creates a changing electric field. It's a very cool thing. A changing magnetic field creates an electric field, and actually a changing electric field creates a magnetic field. So this pulsing current, on and off, produces electromagnetic radiation. And these types of fields, time dependent that is, are more practical than static fields. So we see time, we live in a dynamic world, and we see time changing fields more often than not. And so again, I want to point out that this time changing electric field produces a time changing magnetic field. So we could put B or H here. I guess just to be consistent, I'll put H. So they're mutually reinforcing. So a time-changing electric field produces this time-changing magnetic field, and then that time-changing magnetic field produces a time-changing electric field. And you cannot separate those two things. They're they're two manifestations of the same thing. So, and that is the electromagnetic wave. And so then we bring up Maxwell's equations. How are those things related? So these are Maxwell's equations now in the most general sense. And even though they're in the most general sense, there are still a couple different ways that I could write Maxwell's equations. For example, I could write them in the integral form instead of the point form or the differential form, which I'm doing right now. Okay, or I could express the electric field in terms of the electric flux density D instead of E, which I'm doing right now. Or I could express the magnetic field in terms of H, the magnetic field intensity, instead of the magnetic flux density B, which I've done here. So there are a couple ways of representing Maxwell's equations in the most general sense. Here's just one way. And also, we haven't talked about this this constant C yet, but C is related to epsilon 0 and mu 0, the permittivity and the permeability of free space. And so again, there's a couple ways of representing that thing there. But you see that the electric field E and the magnetic field B, they are dependent on one another in that equation and in this equation. So you see a change, this is a change in magnetic field produces this electric field, and a change in the electric field produces this magnetic field. So in general, these are Maxwell's equations in the most general sense, and in general, E and B cannot be separated. It was only that static case where the magnetic fields and the electric fields were not changing, so that the derivatives were zero, and in that case we can separate Maxwell's equations into pairs of two, and then that allows us to just look at electrostatics and magnetostatics. All right, so the next thing we're going to do is look at the laws that govern this idea that a changing magnetic field produces an electric field. How does that work, right? And those two laws are known as Faraday's law and Lenz's law, and we're going to look at that next. Thank you.